When an industrial induction motor is at a standstill, at exactly 0 RPM, it does not behave like a motor. To the electrical grid, a stationary motor is effectively a transformer with a short-circuited secondary coil. Connecting a load of this size directly to full grid voltage, a method known as direct online starting, forces the motor to draw an immediate inrush current that is 7 to 8 times its normal running load. This massive spike in amperage generates extreme internal heat. Following the principles of I²R losses, the temperature inside the stator rapidly escalates, placing severe thermal stress on the internal coil insulation. That sheer volume of current degrades the local power supply, forcing extreme voltage dips across the entire facility's electrical grid. These sudden sags in line voltage regularly trigger under-voltage protection relays on completely unrelated sensitive equipment sharing the same grid connection. This creates a conflict between mechanical and electrical requirements. The motor needs massive torque to break static friction, but the grid cannot safely deliver that raw current instantly. Large induction motors, generally anything over 5 horsepower, cannot be brute-forced into motion. They require an external starting mechanism to throttle that initial inrush current without compromising the motor's long-term mechanical performance. To bypass the limits of direct online starting, we must look past the heavy cast iron housing and examine the raw magnetic topography inside the motor itself. A standard 3-phase stator is constructed from 3 isolated electromagnetic coils wrapped around a laminated steel core. With 3 individual coils, there are exactly 6 distinct wire ends to account for. These are designated as U1 and U2, V1 and V2, and W1 and W2. In smaller consumer motors, these coil ends are permanently soldered together inside the casing. But in heavy industrial applications, specifically those utilizing star-delta starters, all 6 ends are deliberately kept separate. They are routed out of the stator and gathered together inside an external terminal box, waiting to be configured. Leaving these 6 terminals exposed and independent is the non-negotiable hardware requirement. It is what makes dynamic, mid-operational electrical reconfiguration physically possible. The starting process relies entirely on the first of 2 distinct electrical states, the star or Y configuration. To form this geometry, the physical connection involves shorting the 3 back ends of the coils, U2, V2, and W2, together. This creates a common neutral point, while the 3 incoming grid power lines attach to the outer tips. The physical layout changes the math of the circuit. In this geometry, grid supply line voltage is no longer applied directly across any single motor coil. Instead, voltage dropped across any individual phase winding equals total line voltage divided by the square root of 3. Mathematically, this dictates that only 58% of the full line voltage reaches the motor's windings. In a star configuration, the line current is equal to the phase current. Because the phase voltage was already reduced by a factor of 1 over root 3, and we've eliminated the root 3 multiplier found in delta line current, the total drawn line current drops to exactly 1/3 of the DOL value. However, physical torque is proportional to the square of the applied voltage. Dropping the voltage by the square root of 3 means the starting torque also plummets to exactly 1/3 of its maximum potential. While the motor has less physical pushing power, this 1/3 reduction drastically limits the thermal degradation of the insulation and reduces the mechanical shearing forces on the rotor shaft. The star configuration protects the motor's operational lifespan. By artificially bottlenecking the available voltage, it forces a throttled, manageable current draw during the system's most vulnerable moments of operation. Operating at 58 with 100% of the voltage restored to the coils, the magnetic field reaches maximum density, allowing the motor to generate its full rated torque and finally achieve its maximum running speed. The star-delta sequence isolates starting from running. It provides a protected, low-current acceleration phase, followed by an immediate physical reconfiguration to achieve full power operation. Executing this transition manually with high voltage lines is dangerous and imprecise. The star-delta starter panel is the automated hardware designed to handle this topography shift safely. This schematic outlines the logic required to make the switch. It maps the integration of the main contactor, labeled K1, the circuit fuses, and the critical thermal overload relay, labeled FT1. When the sequence begins, the control circuit simultaneously closes the main contactor and the star contactor, routing power through the U, V, and W lines to energize the motor in the restricted Y configuration. A dedicated timer relay monitors this state, physically holding the star connection closed while the rotor slowly overcomes its initial inertia during the run-up phase. Once the timer expires, it initiates a precise mechanical handoff. It opens the star contactor, briefly dropping the motor into an open circuit state before immediately snapping the delta contactor closed. Throughout this entire sequence, the overload relay FT1 monitors the line current, ensuring continuous thermal protection whether the system is drawing 1/3 or 100% of its power. To prevent catastrophic operator error, the panel features a strict mechanical interlock. This prevents the handle from being manually forced into the delta run position before the motor has properly accelerated. The command circuit acts as the brain of the assembly, ensuring that the transition between these 2 electrical states is perfectly timed. It keeps the system mechanically isolated and continuously protected. The system has a severe engineering trade-off. While the starting current is safely slashed to 33%, The available physical torque is penalized just as heavily, dropping to roughly 25 to 33% of its initial direct online value. This creates a mechanical risk. Every load has a resistive torque. If the resistive torque of the machinery pushing back exceeds the motor's weakened torque in the star configuration, the rotor will stall, the current will spike, and the windings will burn out. Looking at this engineering documentation, the performance formulas confirm the specific math. Because the torque is a function of the voltage squared, the star connection mathematically guarantees this severe drop in rotational force. Operators must carefully calculate the commutation point. This is the exact RPM threshold, where the motor must abandon the star connection and switch to delta in order to overpower the rising resistive torque of the load. Timing is unforgiving. Transitioning to delta too early or too late induces a massive transition spike, a secondary current surge that hits the grid almost as hard as a raw direct online start, defeating the purpose of the starter entirely. Because of this heavy torque penalty, star-delta starters have a strictly defined use case. They are deployed exclusively for high inertia but low starting resistance loads, like massive industrial ventilation fans or completely unloaded water pumps. Beyond the starting sequence, the star-delta relationship can be exploited during steady-state operation to solve a common industrial problem: motors that are vastly oversized for their actual daily workloads. If a delta-connected motor is continuously running below 30% of its rated shaft load, it operates with severe inefficiency. It draws excessive magnetizing current from the grid just to maintain a magnetic field it isn't fully using. Engineers can implement a targeted efficiency hack, intentionally taking an underloaded motor and rewiring it to run permanently in the star connection. By plotting efficiency and power factor against motor shaft loading, the green star curve outperforms the orange delta curve below the 30% threshold. Applying the lower star voltage reduces magnetic field strength, slashing iron core losses, and drastically improving power factor. This is not a marginal optimization. Switching an underloaded motor into permanent star operation regularly yields total energy savings of 10 to 20%. The only physical compromise is a slight drop in rotor speed, usually between 1 and 2%. For applications like centrifugal pumps and fans, this speed loss is negligible, while the reduction in power consumption is massive. The star-delta relationship provides a reliable mechanical method for manipulating electromagnetic impedance to optimize the efficiency of the industrial grid.
Thanks for watching and grow every day with just a bit of information. Like, share, and subscribe for more content and learning.